The test is going to be 65 points. So if you want to give yourself a length of the test. There will be between 8 and 10 multiple choice problems. There will be between 2 and 4, somewhere in that range, 2 and 4 short answers. Okay, those ones where you have parts A and B and you have to answer theoretically. So 8 to 10 multiple choice, 2 to 4 short answer. And then for the mathematical component, you're going to have to do the first 2 and you get a choice of the last 2. So it's going to be 3 mathematical. The first 2 you must do and the last 2 you choose one of them. Okay? So you have an idea of the format of the test. Let's go over some theory that you should definitely know for the test. One thing I mentioned to the other section was this. I know as of right now there are certain people that still haven't turned in the problem set. So there's a good chance I'm not going to put the solution up. Now, what I did for this specific test, because I happened to do it last year, I didn't just do it, I happen to have done this already. I came up with like 10 sample problems for the test last year, mathematical ones, and solved them. So I'm going to put them up on Moodle with the solutions to those. They're just for you to study from, okay? They're not things you have to do, but it might be useful if you do just to look at them. I'm not saying that every problem on there is going to be on the test, because there's like 10 problems. You're only going to have 4 math problems on the actual test. So any of those obviously are fair game, but anything we did in class is also fair game for the math problems. So when you're studying for the math problems tonight, you really want to be studying from your notes, right? From the notes you've done, you've taken. Maybe from your problem sets if you submitted them electronically, you can still look at them. If they're hard copies, obviously you can't. And then also take a look at the sample problems I'm going to put up tonight on Moodle. It'll be under documents and handouts. I'll put up the sample problems, and then I'll put up the solutions. There'll be 2 separate documents. I recommend trying them without the solutions first. See how you do, and then take a look at the solutions.
Are those different from one like you already have up? Because you already have problems up, like practice problems.
Did I?
This section. I saw them last night. I don't know.
Oh, so maybe did I put the answers up though, or not?
Yeah. It was like one complete document.
Was it like 10 problems total?
Yeah, it was like someone on a sleigh, and then it was like 30 degrees.
And then were my solutions all typed up?
Yeah.
So that's them. I already put them up. I thought I had them hidden. I guess they're shown. Whatever. It doesn't matter. On Moodle you can hide documents until you're ready to display them. I must have did display recently. That's good that you looked ahead. Nice.
Thanks.
Smart
A. The whole week is A.
Except for Thursday.
How is that not a good thing? You have a test tomorrow. Why would you not want A?
No, the whole week.
No, Thursday's
It's only-
day.
Sorry, Thursday's the C day. Thursday's different. Is the factory treatment. Alright. So, let's go over some theory. Let's go over some theory. First, the force of friction is depending on what things? Not the coefficient of friction now, but the force of friction. Whether it's static or kinetic, it doesn't matter in this case, but is a function of what things?
Mu and the normal force.
Good. And that's where the formula comes from. The force of friction equals mu Fn. So if I have more rough surfaces, I have more friction. Again, if the surfaces are very rough, I've got a lot of friction. So that's the mu property. If I have an object like this, okay, that we looked at the other day, okay, this object right here, if I add some mass to this, if I add mass, I know that I'm not changing mu, because a moment ago we said mu is only a function of the material. But I am changing the force of friction. Again, if this weighs very little, I'll use Teflon, it's easier. If this weighs very little, look how easy it is to slide around, right? But then I suddenly have 400 grams in there. Is it moving around as easily?
No.
Because there's more FF now. So FF is definitely a function of mass. Well, how does that play a role? Let's take a look. As mass increases, what's happening is the normal force is actually increasing. And think about that. The normal force acting on an empty card is whatever the weight of the card is, right? The weight of the card, say the card is 1 Newton. Well, then the normal force up is 1 Newton. But now let's say I add 2 more Newtons of weight to it. Now the card is a Newton, plus the 2 Newtons of weight I've added to it means that it's pushing down with now 3 Newtons. So now normal force is pushing back up with 3 Newtons.
So the normal force is always going to equal it?
Is always what?
Always going to equal it, whatever it is?
If it's on a flat surface, sure.
Yeah.
That's only on a flat surface. But on an inclined plane or something pulling at an angle, things change. So you don't want to make that generalization. But we know that as the mass increases, the normal force increases. But also we know this. As the normal force increases, the force of friction increases. Again, as mass goes up, there's more normal force. But as normal force goes up, there's more friction. So as a result, we can see how these are directly related to each other. As the mass goes up, in the end, the friction goes up. It's the transitive property of equality. Think about math class. If A is equal to B, but B is equal to C, then aren't they all the same, A, B, and C? So this is the same thing. As mass goes up, friction goes up. Or normal force goes up. But as normal force goes up, friction goes up. So as a result, as mass goes up, we can jump to the end and conclude that friction goes up. But mu is not changing. Mu is not changing. Mu is not changing. All right? It's only changing the normal force, which as a result, or which in turn changes the friction force. All right, so good. Friction is a function of two things, the normal force and mu. All right? The normal force and mu. Let's see. Let's go into the normal force now that we've started with it. What do we know about the normal force? We know several things. Give me one piece of info about the normal force.
The linking variable.
It's the linking variable in our mathematical problems. Very good. That's very important to know. Fn is definitely the linking variable. And Fn always appears in the y direction. So we'll look at the mathematical portion first. So again, mathematically, Fn is the linking variable, and it always appears in the y direction. It also appears in the x direction, right, when you're looking for Ff, but we solve for it in the y direction. Again, we solve for Fn in the y direction and then link it over. What else do we know about Fn?
It's perpendicular to the contact surface.
Absolutely. It's always perpendicular to the surface. So ready? Right now, look at this card. This card is on a flat surface. So Fn acts vertically, doesn't it? But that's for this one instance. What if now the card is at an angle like this? Now which way? Good. Good. Ed, very good. Fn now acts at an angle off the plane. It's perpendicular to the plane, but it's no longer vertical. It's at an angle now. So what we know about Fn is that sometimes it's vertical, right? But it's not always vertical. We also know that Fn is always perpendicular. Always perpendicular. That's why it's called normal. Remember, the word normal means perpendicular in all directions. That's what normal means. A building is normal to the street, because every side of the building is a perpendicular angle. All the sides of the building are at right angles. We also know that sometimes Fn is equal and opposite to the weight of the object. Like right now, Fn is equal to the weight of that object, because the weight is pushing down and Fn is pushing up, and it's in equilibrium. But the minute it's at an angle, or the minute I try to help it by lifting up, Fn is no longer equal and opposite to the weight. So the only thing that we know for certain is that it's at a right angle to the surface, always. That's the one thing we know for certain. Sometimes it's equal to mg, the opposite of the weight. Sometimes that happens, but it's not always true. What we do know for sure is that it's always at a right angle. Let's see what else about the normal force. What else? Yeah, let's see.
So if Fn is equal to mg, isn't Fg also equal to mg?
And that's only sometimes, again. That's not always true. It's at rest on a horizontal surface, and it's sitting there. And imagine there's no force applied at all, nothing else going on. Well, that's Fg, and that's Fn. And that's why that statement you said is true, because ready, watch, Fn minus Fg equals 0. Sum of the forces equals ma, but there's nothing moving, so it's equal to 0. And now if I were to solve this for Fn, I get Fn equals Fg, right? But Fg is the weight of the object. So really, we could say that Fn equals mg. That is true for some instances. Remember, the minute it's tilted, that's not true. The minute something is being pulled at an angle, it's not true. If it's being pulled horizontally, that is true. That is true. Because if an object's being pulled horizontally, my free body diagram changes as follows. That happens, and that happens. Does anything change in the y direction when I'm pulling horizontally? There's no change to the y direction when I pull horizontally. So this statement is still actually true. But if I pull at an angle, like so, if I pull at an angle, now Fn is not equal to mg, because I have to break up Fp into Fpy and Fpx. And now the Fpy component right here is a part of a force in the y direction, so this would change. This would be Fn plus Fpy minus Fg. All right, so I don't want you to make assumptions. So the best way to approach all of these problems is to draw a free body diagram. We went over, remember the steps we went through? Draw a free body diagram, then go to your equations of motion from the free body diagram. So again, this problem, if there were Fp, would change like this. You would now have a Fpy in the beginning, because that's acting up in this problem. So things would change, this answer would change, all of this stuff would change as a result. Okay? Mu. Mu can change only if the surfaces change. So give me an example of a scenario where mu would change.
If you're like walking on tile and then you're walking on carpet.
Yeah, you're walking and you're on a contact surface between rubber and tile, and then you step onto a carpet. You feel more grip on the carpet, don't you? Because there's more friction from the carpet. The mu value would go up. As mu goes up, there's more roughness of the surfaces. As mu goes down, the surfaces are smoother. Smoother, let's use the word smoother. Okay? What about raining? What if it rains? What happens to mu? What happens to mu if it rains?
It's smaller.
Yeah, because what happens? It becomes more smooth or slippery or wet, yeah. So if it rains on the road, and the road has this layer, and we'll talk about, when we get to buoyancy, we'll talk about the idea of hydroplaning and oil on the surface and stuff. I'm not going to go into detail right now for the sake of time. But the idea is that if there's more fluid on the surface, it becomes slicker, so mu goes down. Okay? So concrete versus concrete that has water on it. Concrete by itself has a higher mu than concrete with water on the surface. All right? And this is applied a lot when it comes to cutting things like metal or diamond cutting, because it's a lot of friction that's involved, so they spray water on the surface as the blade spins. So you ever see somebody like a contractor using a circular saw when they're cutting through wood? They don't sit there and spray water on the saw because they can cut right through the wood. But certain applications, they have to spray with water constantly to reduce the amount of friction. They're like granite, yeah. Have you ever seen granite get cut? If you look at somebody cut a slab of granite, they use a blade, and on the blade it sprays water onto the surface there. So it lowers the friction, it lowers the amount of heat that is being released as a function of the blade spinning. Let's see, what else? Oh, what three things are true when you're in a state of equilibrium? There are three things that are true. One of those three things that can be broken into two subcategories. But in a state of equilibrium, what is true? Give me one thing that is true, Victoria.
The net force is 0, or the net...
Yeah, good. The net force equals 0, meaning that there's a balance of forces. So if there's a force to the right of 30 newtons, there must be a force to the left of 30 newtons. That's a state of equilibrium. What else is true? Victoria, again, go for it.
Like when an object is at rest, the normal force and gravity like create equilibrium. Is that like...
That's possible, but that's more. You're being specific. You're looking at a specific instance. I need more generalizations.
No acceleration.
No acceleration. Remember, Newton's law tells us this. F equals ma. If F is 0, well, there can't be 0 mass of an object. It's got to have mass. So acceleration must be 0 for that to be true. So the first two things are linked. Do you see that? If you know the first one, you technically know the second one. If the sum of the forces equals 0, well, that's really just saying that the acceleration is 0. Now, if acceleration is 0, what is true about the velocity of an object? And be careful here. There's two possible answers here. If acceleration is 0, Kev?
Either the velocity is 0 or at constant.
Good. Very good. Those are the two possible cases right there. The velocity is either 0 or it's constant. Or it's constant. So in a state of equilibrium, either the object is at rest or it's moving with a constant velocity. That's what you definitely know. If it's not in equilibrium, then there's acceleration, then there's an imbalance of forces, then there's an increase of velocity, it's not constant anymore, and that's the part of the lab that you saw. Okay, remember in the lab we saw, remember the first scenario? This is lab 4. When you push on the refrigerator with no friction, if you push on the refrigerator, you have acceleration, and you were noticing the velocity kept going up, kept going up, kept going up, until you release the force on the refrigerator and let it go. And then the velocity remained constant, because there was no friction acting on it to slow it down. But the minute you took away the force, you took away the acceleration. But the velocity still remained constant in that lab. When there was friction involved, it was a different story. It was a different scenario. All right? But these are the 3 possible scenarios that occur as a result of there being some sort of force equilibrium in the problem. If we had, and as the rocket travels through space, it burns jet fuel in order to produce that thrust out the back of it, and it follows this trajectory. Now, realistically, in your car, this doesn't really apply as much, but in a rocket, it does. The jet fuel takes up a lot of mass in a rocket. So as it burns jet fuel, what happens to the mass of the rocket? It becomes less and less. So the mass decreases as fuel burns, right? If the force applied remains the same, what must happen to the acceleration for this to be true?
Like it gets or it increases.
Why?
Because like the less mass, the easier it is to, or if it's like the same force and losing mass, then it'll just keep increasing.
Yeah, exactly right. That was that first part of your lab that you saw. And you noticed that when you push the refrigerator with a certain force, and then you push the sleepy dog, remember, with a certain force, and then the textbook, as the mass went down, that acceleration went up a lot. And that comes about because of the following. F equals ma. Again, Newton's laws. Okay, so Newton's laws tell us a lot. If mass goes down, acceleration has to go up in order for the force to remain constant. Again, for the force to remain constant that's being applied, if you have less mass and you're still pushing with the same amount of force, it's going to have much more acceleration. It's like saying if I push on an object like this desk, it's not going to move much, right? The mass is very large, and there's also friction in this case. But then I push with the same force on this, it moves very easily. There's more acceleration because there's less mass. Okay? You should definitely know Newton's 3 laws. I know they were on the last test, but they're definitely fair game. Anything in Chapter 4, because 4.4 is really a culmination of 4.1, 4.2, and 4.3, is fair game from Chapter 4. So you should know Newton's 3 laws, equal and opposite reactions. You should know about inertia, right? The same stuff that you studied for the last test. That's definitely stuff that knowledge needs to be there in order to explain stuff. Okay, in order to explain stuff. What do we know about mu? What can mu not be? This is an interesting thing that we alluded to, but we didn't necessarily state outright. What can mu not be?
Negative.
Negative, good. What else? That's one answer.
It doesn't have any, oh, I forget the word, but sign. Units.
Units. Doesn't have any units. Mu cannot be negative, and mu will not have units. And mu will not have units. Mu will also not be greater than 1. Okay, so mu, if you want to make a statement, mu is a decimal that ranges between 0 and 1, but not including 0 and not including 1. You can't have 0 as mu. That means there'd be no friction. Okay, you can get close to it. Theoretically, you can get close to it. When you're in space in a vacuum, you actually have 0. But we're talking about on Earth, okay? So mu is between 0 and 1 exclusively. So not including those values, 0 and 1, but between there somewhere. Let's talk about static friction for a minute. Let's talk about static friction. It takes on a range of values. It takes on a range of values. So let's say I'm pulling on this object with a force of 20 newtons. And it won't budge. The object will not move. I'm pulling with 20 newtons. It won't go anywhere. Why not? What's pulling back against it?
FFS.
Yeah, FFS, which is also 20 newtons. All right, so it didn't work, and I failed, and I can't move the couch. So I go downstairs, and I get my brother, and I say, James, come help me with this. Help me pull on this couch or move this couch. So now together, me and James apply a force of 30 newtons. All right? We apply a force of 30 newtons. And you know what? The couch still doesn't move. So what's friction now? Josh? What is it? 30 newtons. All right, you know what? It's still not moving. I get help from my other brother, Joey. And I say, come help us move this couch. And we try to push it. And it's still not, we'd be really weak if this was true, by the way. So we then push on it together. And the three of us push with 40 newtons of force. And it still isn't moving. Well, what's friction now? 40 newtons. What does this explain to me? What am I getting at? What am I trying to allude to?
Like the FS max is for the max.
Well, it's still not moving though, Victoria. It's still not moving. What am I alluding to? Paul?
That FFS is a range.
FFS is a range of values. It depends on how much force you're pulling. Now, how would I know when I've reached FFS max, Victoria?
When it begins to move.
Yeah, as soon as it begins to move. Let's say now, hypothetically, all right, it took 42 newtons to move it. That's what it ended up taking, 42 newtons. Then I know as a result that FFS max is something less than 42 newtons. That's all I know. I don't know that it's exactly maybe it's 41.9. Maybe it's 41.99. Maybe it's 40.7. Okay, maybe I didn't check numbers like 41. Maybe I went from 40 right to 42. All I know is that if it begins to move at 42 newtons, it means that the maximum friction can push back with is at least, or is at most, 42 newtons. It might be less than that. All right, so if it took 42 newtons to get it moving, friction at most could be 42 newtons. Static friction. Okay? At most. That's why I put less than 42 newtons.
So then could you just give some really large number and just say that that's the maximum? If you say you went from like one end wasn't moving and then you went to...
Sure, but that wouldn't be realistic in a lab, exactly. Theoretically, sure, Ed, but you would never do that.
Test would you not count?
It wouldn't make sense. It wouldn't make sense to be an answer. Why would you go from 1 to 500, right? That's why in your lab I kept telling you guys, try numbers to see what FFS is. Remember you kept trying numbers to see? You kept changing over and over. Increase by 10, increase by 20, increase by 30, increase by 40, and so forth until it started to move. And then you could break it down into smaller sub-intervals. Okay? But the idea is conceptual, that FFS takes on a range of values based on whatever FP is in the problem. Okay? What is a scale reading when you step on it? What is a scale reading? Those that did that extra credit, I should see hands shoot up right away. Those that did that extra credit, I've seen 1 or 2. Okay, what is a scale reading?
Isn't it your mass times the gravity?
So it's reading your weight, absolutely. It's reading your weight. But we notice that can fluctuate, right? So if I suddenly, grab a table and pull up on it or push down on it, I'll see the value change on the scale. Or if I'm on a moving platform, like an elevator, I see the weight or the value of the scale change. So what is it really reading? What is it really actually reading?
Is it kind of like the force of gravity on
That's what he said, the weight. That's the same thing, force of gravity. It's not really reading your weight. It's reading the normal force. A scale really reads the normal force. So think about it. If I step on the scale and I'm not moving and I'm standing still, then sure, he reads my weight, which is equal to the normal force. That's what the normal force really is. But now, watch what happens. I grab onto these and I hold these now. These are not part of my weight, but they are pushing down, aren't they? So that makes the normal force push up with more of a force when I hold these. So the minute I hold these on the scale, now I weigh more according to the scale, because my normal force is increasing. Or, if I'm on an elevator, and I'm standing still, and the elevator starts to move, acceleration pushes me upward, which pushes on my legs a little bit more, which is why the scale reads a higher value when the elevator starts to move initially, when you're moving up, because of that acceleration. So a scale is really reading the normal force. Okay, really reading the normal force. What would happen if I was on a scale and I like jumped off the scale? Don't I have to push down the scale to jump off of it? So I'd be pushing down in addition to my weight. So what would happen to the fluctuation of the weight or the normal force or the scale reading? What would happen to it?
It would be very high.
And then when I got off the scale, what would
It
happen?
would be very low.
Yeah, it would drop down to 0, right? So if I'm on a scale and I go to jump off of it and push off and go to the right or something like that, I'm going to see a fluctuation for sure. Or if I'm on a scale and suddenly somebody walks over and starts to help lift me up, and they like walk up to me and like hold on to my waist and try to lift me like a ballerina or something, right? Try to lift the person. If you're pulling up on the person, well, you're lessening what the scale has to push back with now. So the normal force would go down. So you see the scale go down. So the scale is really measuring normal force. Okay, normal force. Hey, does that answer your question or?
No, I was just going to say, so when we did the elevator thing, it said that our weight was actually lower, but in reality it was actually less, it was just the normal.
Well, it's this, your weight is the same. Your weight isn't really changing. The normal force.
At that moment, you were kind of lighter than you were because the acceleration was pushing you, I don't know.
Well, if acceleration is up, then your normal force increases. If acceleration is down, your normal force decreases. That was the general trend that we figured out from that. Okay, that was an example, like, I don't know, 3 or 4 we did, I think, that had that. Okay. Where was I at? That was normal force. Inclined planes. That opportunity tonight to look at it. I can do maybe 1 or 2 if we have time, but a lot of the conceptual part of this test. Let's say we have an inclined plane like this. And here's an object and it's sitting there at rest. What could I do to cause this object to start sliding down the ramp? Tilt the ramp, right? Make the ramp like this now instead. And maybe now it falls down the ramp, right? So theoretically, I'm increasing the angle theta, right? So if I want something to move down a ramp, I want theta to go up. Right? Where this is theta, obviously. Theta 1, theta 2. So if I look at this and think about this physically, what's happening, and I went over this with the other class. It's really important to get this piece. Let's talk about this. On an inclined plane, and this is difficult, you have to recall your notes. It might not be off the top of your head. Remember, this was FGX, and this was FGY. This was normal force, and this was friction. That was the free body diagram of any inclined plane. I highly suggest, by the way, tonight, that you just look at least at the last 2 examples from 4.4 to understand inclined planes. If you can do those, you should be fine for the test for the inclined plane problem. But this is the formula, or this is the equation of motion, or the free body diagram, the free body diagram that gives us the equation of motion. What is really pulling this object down the ramp? Which of these 4 forces? FGX. FGX is what's really pulling this down the plane. So really, when I'm increasing theta, I'm really increasing FGX. That's what's really happening here. As I increase that angle, as I take my hand and I have my stylus here, it's not moving, it's not moving, it's not moving, it starts to move. I'm increasing FGX. I'm making FGX stronger. And the way I can determine that, I can prove that to you mathematically. If you remember, the formula for FGX is really like FG cos of 90 minus theta, which is really mg cos of 90 minus theta. All right, this is really what FGX is. And this is something that I went over in class that I'd recommend just memorizing this for now, actually. I'd recommend this one of the few things I'd memorize. It's not on your formula sheet, but maybe it's useful. You don't really have to memorize it if you remember that FG in the x direction means this, but then FG itself really means mg. So you can memorize one little piece and then just substitute for mg. Now, what you'll notice is this. If you had a certain amount of mass, let's say the mass was 7 and gravity was 9.81, all right? And you have cosine of some angle. If you fluctuate that angle and keep increasing it and make theta bigger and bigger and bigger, you're going to see FGX get bigger and bigger and bigger. And I had the other class try it out. We can check it tonight for the sake of time. If this value is like 10 degrees, here's the ramp. 20 degrees, 30 degrees, 40 degrees, 50 degrees, 60 degrees, 70, 80, 90 degrees. as this value of theta gets bigger and bigger and bigger, you're going to notice if you try numbers like 10, then try 20, then try 30, your overall answer will get bigger and bigger and bigger. What you're doing is you're really increasing FGX, which is the component of weight that acts down the ramp. Down the ramp. Right? FGX, you might want to jot this term down, right? So we know what it is. FGX is the component of weight that acts down the ramp, or acts parallel to the ramp. What's FGY called? How would you describe FGY? If FGX is the component of weight that acts parallel to the ramp or down the ramp. How do you describe what FGY is? What is FGY, Paul?
It's the component that acts perpendicular to the ramp.
Yeah, the component that acts into the ramp perpendicularly. FGY, I'll go back to my free body diagram to see this. FGY is the component of weight that acts into the ramp perpendicularly. And you can see that right here in the free body diagram. We talked about the force of gravity being different on different planets. Force of gravity being different on different planets. How does that relate to this topic? Give me an explanation of that, or an example of something like that. What's an example? You did this in your lab also, where you changed it to Jupiter suddenly. What happened as a result, right? How is that related?
Well, if gravity changes, then Fn changes, meaning the angular function changes.
Yeah, so if you think about it, if gravity changes, right? Line load, there we go. If gravity changes, and we have an object that's in a state of equilibrium, well, then that's also going to affect the normal force. So if I have a smaller g value, and we know that, so that decreases, and we know that the mass is constant. Okay, if g goes down and the mass is constant, then Fg, the weight of the object, has to also go down. So this explains why if you're on another surface or another planet, objects will behave differently. So an object that we're able to jump 10 feet, or a person that can jump 10 feet on Earth, let's say a long jump, or even actually a high jump, that'd be crazy. A vertical of, like, let's say 3 feet, they have a vertical of. They probably have a vertical of like 25 feet on something like the moon, provided that they were able to not have like a spacesuit on, obviously, you know, that kind of stuff. That would change it, right? Okay, or on Jupiter, it'd be the opposite. Jupiter's gravitational pull is almost triple ours. So you would jump, if I could jump 3 feet, now I can only jump 1 foot, or 1 foot rather. Whatever. 1 foot on Jupiter. Yeah.
So that's like constant?
Constant. C-O-N-S-T.
Oh, what's the
I
last
put a period. Decrease.
Oh.
Okay, if little g decreases and the mass remains constant, the weight, Fg, must decrease. Now, here's the thing that I need to point out, because I noticed on a lot of your homework this mistake. The problem gives you the weight of the object. So say the beginning of the problem says, the weight of the object is 37 newtons. What is that as a variable? Ed?
Isn't that just Fg?
That is Fg. Again, if a problem says the weight of an object is 37 newtons, you know it's a weight because it's got newtons, or you know it's a force because of the newtons there. It can't be a mass. This has got to be the actual weight of the object. If it said an object has a mass of 37 kilograms, well then that is the mass of 37 kilograms. They're two very different things. Mike, how do I go from mass to weight? How do I go from mass to weight? What's my formula? Fg equals what?
Fg equals mg.
Mg, there it is. So if you're given the mass, Mike, what should you multiply by? So you're given this.
The gravity.
Yeah, multiply by 9.81 to get the weight. Remember, when you're given the mass, multiply by 9.81 to give yourself the weight. If you're given the weight, how do you get the mass? Yeah, who said it? Divide. Good, Steph. Divide by 9.81 in that case. Think about it for a moment. Instead of giving the mass, say you're given the weight of the object, and you're told, well, the weight of the object is 30 newtons. That goes right here. And if you want to find the mass, you just solve for m. Just solve that equation for m. That's how you would get the mass. So you would divide by 9.81 to get the mass, if you're given the weight. This might be important. If you're given the weight of an object, but you need the mass later in the problem, it might be useful just to divide by 9.81 in the beginning and list the mass of the object in addition to the weight of the object. Okay, both of these two things are important. All right, let's do a mathematical example. Pulled at an angle, all right? Being pulled at an angle, because this is what we did maybe like, a section and a half ago, kind of. For studying techniques, you should definitely be able to do simple problems where it's pulled horizontally, all right? You should be able to understand the difference between static friction and kinetic friction if it's moving or stationary. You should be able to do a problem that's pulled at an angle, and you should be able to do a problem that is on an incline. Okay, obviously you'll be able to omit one, but I'm not going to tell you which one for that reason, so you study them all. Okay, so let's take a look at an example where it's pulled at an angle. Let's say an object is pulled at an angle of 30 degrees above the horizontal. Okay, with a force of 40 newtons. And the object's mass is 10 kilograms. We know that as a result of this pull, the acceleration the object feels is 0.8 meters per second squared. Our goal is to figure out mu. Am I looking for mu k or mu s based on this problem? And use the context clues to help you. Paul? Why? Yeah. Again, you have acceleration means you have motion. When you have motion, it's kinetic friction. If it were stationary, what kind of friction would it be? Yeah, static friction. Good, static. So, if we're given the mass of the object, right away, what can we figure out about the object? F what? Fg. You can figure out the weight of the object right away. Now, we're going to look at our equations of motion. Let's go ahead and do that. So, acting down is gravity. Acting left is friction. Acting up is normal force. What's the deal with this Fp? What do I have to do to it? What do I have to do to it? Marianne? Yeah, I got to do this. I got to write Fpx here and Fpy right here. And then I can do this. I don't need it anymore. We're done. Okay? Provided, obviously, I wrote it down somewhere else. What was it? 40 newtons, and the angle was 30? Okay, these are all my givens on the right that I'm listing there. So I can break it into its components. Why do I know that Fpy is up and Fpx is right? How come?
That's the way that you're calling it?
Yeah, what if I was doing this? Let's say, hypothetically, I was like one of the football players at practice and I had to pull one of those sleds. And they hold on to like ropes maybe, and the rope is attached at an angle like this, upward. Okay, the rope is attached to my body, a harness, and it's attached to the object, and it's going up, and I'm pulling and dragging the object behind me. I now be pulling to the right, but I'd be pulling instead of up, I'd be pulling down. So it depends on the object. If this problem said there's a force being applied at an angle of 30 degrees below the horizontal, then the angle would be down here. And I would have this kind of a scenario. You don't have to draw this. It would look like this. That would be Fp. And now Fpy would be acting down in the problem. Okay? Use these four, or in this case 5 once you've broken it up. These two for the x direction. Set it equal to m times your acceleration. And in the y direction, sum 1, 2, 3 things together and set that equal to 0 for the y direction.
Did you
I think I got to the end of it, but I didn't put numbers in, so you can see the rest of it.